What's up, everyone? We are back with another Tesla Mechanical Design Engineer interview question solved. This problem came directly from a Tesla Mechanical Design Engineer interview exam, which is administered before a couple of technical interviews. So without further ado, let's jump right in. Step 1 for today's problem will be to review the problem. Step 2 will be determine our equations to solve the problem. And step 3 will be attempting our solution. Beginning with step 1, the problem states a positive displacement pump provides 3 times 10 to the negative fifth meter cubed per second flow of water of kinematic viscosity 1 times 10 to the negative 6 meter squared per second through a pipe of 3/4 inch inner diameter over a length of 10 meters. With an expansion to 2 inches outer diameter into open air, what is the change in pressure of the 10-meter pipe? Alright, beginning with step 1, the important information in this problem statement is, first of all, that our positive displacement pump provides 3 times 10 to the negative fifth meters cubed per second flow of water. So that's going to be our flow rate. Our kinematic viscosity is equal to 1 times 10 to the negative 6 meters squared per second. Our inner diameter is 3/4 inches, which we can convert to 0.01905 meters. And our outer diameter is 2 inches, which is equal to 0.0508 meters. Finally, we're told that the fluid in our pump is water. Now, because it's water, we know that the density is going to be approximately 1,000 kilograms per meter cubed. Let's move on to step 2, identifying our equations. Well, because this is an internal flow problem, or we have a fluid flowing within a contained structure, we want to look up our internal flow equations. For all internal flow equations, the first thing we want to do is calculate our Reynolds number. This is a dimensionless number which gives our inertial forces over our viscous forces. And it's important because it can tell us if our flow is laminar, transitional, or turbulent. And that's going to determine or dictate the equations that we use. So to calculate our Reynolds number, we need to know our average velocity times our diameter over our kinematic viscosity. But we don't know what our average velocity is. So we have another equation for that, which states that velocity is equal to flow rate over area. And intuitively, that makes sense because we're taking meters cubed per second and dividing them by meters squared, so we're going to be left with meters per second, which is velocity. So doing that, we get 3 times 10 to the negative fifth meters cubed per second over our area, which is pi r squared. So that's pi over 4 times the diameter squared, 0.01905 meters. And that gives us 0.1053 meters per second. So that's going to be our average velocity. Now that we know that, we have everything we need to find our Reynolds number. So plugging everything in, we get a Reynolds number of approximately 2,000. So for a Reynolds number that's less than or equal to 2,300, we're going to have laminar flow. Anything that's greater than or equal to 4,000 is turbulent flow, and anything in between is transitional. But we're dealing with laminar flow in this problem. Now, the next thing we need to do is determine our entry lengths, because this can affect how our fluid will flow throughout the system. Because our pipe length is much greater than our diameter, that is more than 10 times greater than our diameter, our entrance effects can be neglected. They're not really going to affect the system. So let's move on to finding the equation that we can use to solve for our pressure drop. For a laminar flow pressure drop, one of the equations that you might find when you do a quick Google search is that change in pressure is equal to 128 times our dynamic viscosity times flow rate times length over pi times our diameter to the fourth. This is pretty awesome because we can solve for all of the terms in this equation. The only thing we don't know is our dynamic viscosity. But dynamic viscosity is just equal to density times kinematic viscosity. So solving for our dynamic viscosity, we find that mu is equal to 1 times 10 to the negative third Pascal seconds. Now all of our unknowns are solved for, and we can simply plug and chug. So putting all of the information into our equation for the change in pressure, we find that delta P equals 128 times 1 times 10 to the negative third Pascal seconds times 3 times 10 to the negative fifth meter cubed per second times 10 meters divided by pi times 0.01905 meters to the fourth. All of those terms are going to cancel out, and we're just going to be left with 93 pascals. Indeed, pressure is measured in pascals, which is force over area. So it looks like everything is working out for us, and I think we can feel pretty confident in this solution. That's all for this one. I hope you enjoyed the video. If you found any issues with the problem, please leave a comment below, and please like and subscribe. We'll catch you in the next one.